Today. My name is Lawrence Edmond IV, and I'm currently a rising senior at UC Berkeley in the Department of Astronomy and Astrophysics. And I want to talk to you guys a little bit about the project that my mentor, Dr. Maria Okanova, and I have been working on this whole entire summer titled Tracing Null Geodesics Near Black Holes. So just to run through the methodology real quick before I start talking about the more of the theoretical and conceptual motivations behind my project. The overall goal of the project this summer was to use a portion of the SpEC Numerical General Relativity Code to study the geometry of regions of extreme space-time curvature near two types of compact objects. The first case is an isolated spinning Kerr black hole, and the second case is a non-spinning binary black hole merging event between two Kerr black holes. And in order to perform these types of calculations numerically, the first step that I needed to do was essentially derive an expression for this thing called the metric tensor. I'll go more in depth about what that is and what it means in a form that could be plugged into a computer essentially and solved numerically over some given time domain. The next step was I need to apply that 3+1 expansion of the metric tensor to the SpEC code to begin calculating a large sample of trajectories that essentially would follow the path that light would take through these intense regions of the space-time curvature. After that, I had to go in there and essentially use a type of ray tracing algorithm to follow these trajectories from an outside observer back to where they came from to begin to get a better idea of exactly what an outside observer would see near these types of compact objects. And finally, I wanted to plot those results so that way we could just literally see the path light takes. So before I start going into detail about all of that stuff, I want to do a brief review of what special relativity is and how to generalize special relativity to get the very well-known theory of general relativity, or GR. So first of all, special relativity, SR, is perhaps one of Einstein's largest contributions to the world of physics, in the sense that he showed that the laws of physics should all remain constant for observers in different, quote, inertial frames. Essentially, what that means is that I'm going to bring up the classic train analogy. One of the most fundamental laws of physics is that the speed of light should remain constant to all observers, regardless of their own motion. Essentially, what this introduces in terms of reality is the faster you go, distances and times begin to contract and expand to adjust for this change in your essentially inertial frame of reference. So in this diagram that I have here, I have your standard space-time diagram with units of CT, which is just a distance representation of time, of the time dimension on the y-axis, and a positional vector on the x-axis. T prime and x primes are the distorted coordinates according to how fast an observer is moving. And as you notice, as the speed increases or decreases, the coordinate grid begins to contract or expand. Einstein wanted to take this theory and expand it to any arbitrary coordinate system, not just the one that you see on screen. And essentially, the way he was able to do that was he said, consider any kind of arbitrary geometry, and then increase the speed progressively over a period of time. If you were to take this situation and chunk it up into little time pieces, you would be able to find that the geometry of the entire coordinate system would change momentarily and incrementally for each time step. And then after doing a whole bunch of highly complicated math, he was able to essentially connect these changing coordinate systems in a very nonlinear fashion that started to show things like the emergence of the force of gravity through the space-time curvature in these different geometries between different, basically, time slices of space. So let's talk a little bit more about how we can plug this into a computer now. So like I said, one of the main purposes of this project was to use the SpEC Numerical Relativity Code to study regions of space that we cannot solve analytically. One such example of this would be binary black holes running into each other. The reason why this is a very difficult situation is because each black hole has its own metric, the space around the black holes have their own metric, and the final black hole has its own metric. And each of those three metrics, or four metrics, are going to change over time as the objects get closer and closer and closer. is going to produce a whole bunch of interesting phenomena like gravitational waves and all that. However, you cannot solve this problem analytically because normally the space-time metric is a static mathematical object that does not evolve over time. So let's talk about how we can, first of all, exploit the metric's static capabilities by chunking up time and parameterizing or quantizing time, essentially. So here I have a image of the space-time metric, G sub mu nu. I have G sub ij there, which is a typo that's not just, I don't want to distract too much away from it, but just for like, in terms of the field, they use Greek letters mu and nu to consider a 4D space-time metric, and they use Latin indices like I and J to consider just the spatial components. But more importantly, what the space-time metric actually is it contains all of the necessary information to describe some region of space-time. So if you see this image that I have on the bottom right side of the screen over here, I have three spatial planes per se, stacked on top of each other. You can consider, or these planes are called hyperplanes, and every single one of them, planes 1, 2, and 3, are going to have different spatial metrics. These spatial metrics are then going to be, or you can connect these spatial metrics mathematically through this thing called the Christoffel symbol, which is this expression right here. And essentially what the Christoffel symbol does is it contains the information necessary to draw that path between planes 1, 2, and 3 that you see on the screen. And the curvature within this path is essentially what causes the force of gravity. Very generally speaking, it goes much more in depth than that, but got to keep on moving. So now with this concept of curvature in mind, one thing that you can actually do is exploit the fact of moving a particle along this curved path between different hyperplanes to essentially track the motion of physical massive or non-massive objects moving through that region of space-time. If you want to do the standard derivation real quick, you have to use this mathematical concept called parallel transport, which is expressed by this equation up here. You apply the parallel transport equation to the tangent vector of some arbitrary path to simplify this problem out of this ridiculous differential geometry 4D space. Essentially, all you're doing is moving the derivative of a line along another line to see how the line changes. That's it. So apply the parallel transport expression to the tangent vector of the path x lambda up there, and then you get this expression right here. Your whole point is studying the direction light takes, which means it's going, and since light is one of the fastest moving objects in space, it will follow the shortest path, which means all you have to do is minimize this parallel transport equation right here, or set it equal to 0. Inside of the parentheses is an expression that's similar to the covariant derivative of this vector, which is expressed by equation 3. Use that to expand it all the way out, do a little bit of algebra, and you end up with this equation down here, which is referred to as the geodesic expression. The geodesic equation can be solved analytically for some cases to trace the path of light through curved space-time, and more importantly, you can express it in terms of the momentum of an object over here in equation 8 to use it numerically to solve the paths of light around much more complex versions of space-time. So fast forwarding a little bit, now we're getting to the SpEC code. So the SpEC code essentially applies all of the mathematical motivation or all the mathematical concepts that I just said into a computer simulation where essentially it places a black hole in the center of an arbitrary grid and it places an observer some distance away from that grid, right? It then goes in and uses a numerical algorithm to solve the momentum version of the geodesic equation down here for a large number of photons. It then determines which photons reach the observer and ray traces their trajectory back to where they came from to develop the path that light took around that space-time. So here's one of the simulations that I made just as a test case. And as you can see, you have the photon of light originating from the backside of the black hole. It is following the shortest path around the space-time geometry, being brought all the way around the backside of it and reflected back up towards the camera, which is showing the extreme gravitational lensing that some of you may have seen in the famous movie Interstellar with their black hole. So we expanded this out a little bit further, and I did multiple simulations, essentially, just so different types of phenomena that could occur around black holes. Right here, you have a couple of examples of photons that would orbit around the event horizon. Here you have an example of a innermost photon orbit at the bottom of the black hole being projected upwards towards the observer. And you also have large gravitational lensing effects appearing from the negative z direction. And then on the far right side of the screen, I also have just a standard edge-on view of a black hole with the standard accretion disk, or where the accretion disk would be. And the more interesting cases is exploiting the ability of computers to basically solve things very, very quickly for us. And I was able to generate some plots of the trajectories that light would follow around binary black hole mergers. So on the left side, we have an edge-on view of just once again some gravitational lensing. We have a couple of photons emerging and following the black holes as they go through space before they merge and then coming out and heading towards the camera. So these are all on the order of a few minutes, just right up before the merging event occurs. Yeah. And so, yeah, these are just a couple of cool pictures that we were able to come up with. And with that, I just want to say thank you to the NSBP, especially to Casey for helping pull this entire thing together and giving me one of the best physics experience that I've ever had. And thank you to all of my friends that I've made up here for keeping everyone motivated. We did great. And everyone's presentation so far has been amazing, and I can't wait to see the rest today. So, any questions? This would be my fourth. This would be the fourth.
So this looks like this works. This code needs a time-dependent metric.
Yes, it does.
So you can use this if I want to do all tests of deviations from GR. Anything that gives me a metric, I can plug in.
Yes.
This, right? So
exactly.
Right. I know a guy who does turn Simons gravity. Yeah, Masha made her living so far doing that too, right? So, yeah. No, but it's yeah. So that go.
Yeah. Do you have another question? Okay.
Yeah. So actually, David beat my question.
Could you use your seat mic, please?
Does that work now? Oh, look at that. Oh. Okay.
How do you move? All right.
Can you hear me now?
Yeah.
All right. Two questions. So I like your description of parallel transport. Now there's a very deep connection between parallel transport for an arbitrary vector field, you know, that you move. And I like your thing about holding up a flag, moving in a roller coaster ride, and keeping the flag nearly parallel, which is the same thing. There's one object, though, that is perfectly parallel transported. This is a trivia question. There's one object that is perfectly parallel transported, and it stores within it a principle of general relativity called the equivalence principle. What is the object?
Object.
If I act on the covariant derivative on it, on this object, and it's exactly zero.
The space-time metric.
Exactly. Yeah. Beautiful answer.
Yeah, the space.
That's exactly that is the statement of the equivalence principle.
Right. And that is actually that's expressed in equation 5 up there, using the 3.
Where's equation 5?
Equation 5, right up over here. I have the 3+1 expansion of the space-time metric in terms of the lapse rate, the spatial shift.
No, the equation 5 is just
yeah, just an arbitrary.
Right. So it's the statement of that is zero.
Right. Exactly.
Okay.
Mostly because we're looking at the
okay. But yeah, going back to that's a very interesting because modified theories of gravity, for example, like that may necessarily not be the case. That's
really?
Yeah. So that's what's interesting. Some modified theories of gravity, the strong equivalence principle, not the weak, may not necessarily be obeyed. In fact, the very first version of Chern-Simons gravity with Jacques, that was actually the case. So anyway, that's an interesting thing. So the second question I have for you is, what do you plan on doing in your future?
This, and also I want to work on numerical relativity. I want to go into theoretical cosmology, and I want to study gravity in a little bit deeper capacity than this. I don't know if I want to study quantum gravity yet, only because I don't know if I agree with the concept of trying to quantize gravity per se, but I think it's definitely something I want to look into. But in general, I just want to fight with gravity and the concept of time for the rest of my life.
Okay, that's a good fight to be in.
Oh, yes.
All right. Good talk.
Other questions?
Well, no one else. One thing I know.
One thing I notice as students, right? So I'm hearing some commonalities, and so I just want to say it out loud. And that is that, you know, you start doing research and someone says, hey, here is a code, run these simulations. We want to do this comparison. And the next step, someone says, hey, here are these equations, these integral equations, write a code to solve them and run these simulations. And then they say, hey, here's a physical situation. Write down a set of differential equations, then, you know, put them in coding form, and then, you know, give us all these visualizations. And then they might say, now build this thing, right? So you guys are a lot of, here's the code. So in terms of where you see yourself next, in terms of here's a situation, I mean, where do you see your...
Yeah, so one thing that I really like about physics is that you can use math essentially to tell you what you should be looking for in real life, right? So I think simulations like these could give us a new means to start trying to figure out or trying to observe these binary black hole mergers, and ideally more of an observational point of view instead of LIGO, where it's more so indirect. I don't know if that's possible at all, but it could be interesting because
electromagnetic.
Exactly. Like simulations like these help us understand what gravitational lensing would look like. And now we use that all the time to discover a number of things in observational astronomy, right? So I'm trying to figure out a way, if it's even possible, to study black holes from a highly theoretical point of view and then expand that out to some type of observational project.
There's a recent result where people have seen
right. Right. But no one has done it yet for these cases. Right.